All right, let's get going. I don't know where everybody else is, but I'm here. I think I spoiled you guys, not you personally, but the class because of my YouTube postings. If they can't make it or don't feel like getting up, they can always go to YouTube, which I guess is a good thing because I'm here to help you learn chemistry, not make you force coming to my Zoom meetings. So with that, let's get started. Good morning, everybody. Hopefully you're ready for another exciting morning with your host, me, Dr. White. Hold on. Start out on a good morning. And a couple things. First of all, I'm very happy. Why? Because this morning I uploaded to the assignment area lab number 7. Because if you try the Labster for lab 7, I don't have to say anymore. Yep, I see people are agreeing me out with me. And I decided, I'll write my own lab. And because I'm a PhD chemist and I know how to use this, I did. And it came out very nice. You'll let me know if you like it or not. And I'll go through that tomorrow. All right. What I promised I'd do today, so I better get to it, is I promised I would first go through the problem set for chapter 6, which is on Blackboard. And the first thing is you should know what a mole is. One definition, hold on, let me just check something real quick, my way of checking. And it is on the screen. I finally figured out how I could do that without the thumbs up, people, but not to let you feel left out. Everybody see chapter 6 practice problems? Thank you, thumbs up, people. Don't lose your thumb. We need it the rest of the semester. Uh-oh, look out, it's Awful Humor Wednesday. All right, let's get to work. One definition of a mole is, and I don't know why this is not giving me an arrow. And I'll work it out later. You'll have to deal with the little circle. But anyways, one definition of what is a mole is a chemist counting unit. And there are others too. You could also put down a mole as Avogadro's number. A mole is equal to the molecular weight of a compound. A mole is equal to the atomic weight of an element. And a mole is equal to Avogadro's number of atoms for an element, of molecules for a compound. So there are many definitions. They're all true. What is a mole? Now, you should know in honor of someone who played an important role in a mole is what is Avogadro's number? 6.02 times 10 to the 23rd. Now, the next questions deal with the following concept. And that is, let me check, is that, yep, it's on. That is 1 mole of an element equals Avogadro's number in atoms. 1 mole of a compound equals Avogadro's number, 6.02 times 10 to the 23rd, molecules of that compound. And remember, this is a calculated number, so 6.02 times 10 to the 23rd is 3 significant figures. I might have mentioned long ago on a website, I found someone who was a reputable website, so I believe the number had Avogadro's number to 18 significant figures. Why someone would need that, I have no idea, but it is out there if you ever do. I don't, either do you. So let's go back to the problem set. And the first one is how many atoms are in 6.574 moles of sodium? What are you trying to find? Atoms of sodium. What are you given moles? And it's time, oh, I have to do this. It's time to use your good buddy, your good friend, you know it's coming, unit analysis. It's been my good buddy, my good friend for many decades. Oh, I shouldn't have said that. Wait. But anyways, let's get to work. We start with what we have, moles of sodium. We look at what we're trying to get to units-wise, atoms of sodium. Use a ratio. Atoms of sodium goes on top, moles go underneath. Anything divided by itself becomes number one. And where do you get this ratio? 1 mole of a compound equals Avogadro's number. Do the math, 4 significant figures. The 1 is the exact number. This is 3. The answer is 3 significant figures. Let's look at number 5. How many moles are 3.000 times 10 to the 14th atoms of silver? What are we trying to find? Moles of silver. What are we given? How many atoms? This is the only number we have to start with. We're trying to get to this unit or for our answer. Once again, oh yeah, we use unit analysis. Whatever we're trying to get to goes on top of this ratio. Whatever we're trying to get rid of goes underneath. Where do we get the numbers that go here? 1 mole of a compound, or an element in this case, equals Avogadro's number, 6.02 times 10 to the 23rd. And this is 4 significant figures, 3. When you multiply and divide, your answer should have the same number of significant figures as the number with the lowest, which is this case 3. And here's the number, 4.98 times 10 to the minus 10. On test.
Hi, Professor. I have a question.
I do questions.
According to my, so I try to do it by myself, and my response is, in the end, 4.98 times 10 in the power 36. Where did I do the mistake?
All right. Let's go through it the long way. Hold on one second. And thank you for your question. Remember, in my class, all questions are good questions. Hold on while I'm waiting for my spreadsheet to show up. Hold on. If you were in class, you'd be waiting while I'm doing formatting cells. Hold on one second. I just need to write this down. All right, let's make this larger. First of all, I did get the right, I think I got the right answer. It would be 4.98 times 10 to the minus 10th. Let's go back here. I did. What I think you did was you missed the 0 that was on your calculator. Either after class today or in my office hour tonight, we'll work with your calculator and I'll help you out, okay? Okay, thank you. Once in a while, remember, I mentioned it first day, and you've already seen it more than once. Dr. White does not walk on water, even when it's frozen. And therefore, I will once in a while make mistakes on calculations or other things on practice problems. It's few and far in between. Did I tell you guys that I do? Did I tell you guys the story about my PhD thesis and the advice my advisor gave to me after I got my PhD? I was very fortunate to have Dr. Roosh as my advisor, being part of his research group. And after I got my PhD and I was about to leave town, I had a talk with him. He said, I want to talk to you. And he thanked me for being in his group. It was a really nice chat. He said, I have some advice for you. I said, what? Never, ever open your thesis again. I said, why? Because you're going to find a mistake. I proofed it. You proofed it. My second reader, another faculty member, proofed it. I had in my research group 4 of my colleagues proof it. I even proofed it where I read it backwards, 1 line at a time. About a year and a half later, I had friends over and I had it sitting on my coffee table. Oh, is that your thesis? And we opened it up and immediately I saw a minor mistake. Blech. Minor, but it's still in my mind, it's a mistake. About 2 years later, same thing, opened it up. Someone, oh, is that your thesis? Found a mistake, different mistake, minor, but still a mistake. It's no longer on my coffee table for people to open up. And it's been long, long time since I've opened it up, and I won't. Let me just do something really quick. All right. Shahana, thank you for, you're correct. But most of us will be doing it on a calculator. So like I said, if you ever have problems with your calculator, either after class, I'll always stick around, or in my office hours. All right, let's move on, because I do want to get you out of here before midnight. I'm just joking. I want to get me out of here before midnight. All right, let's move on. Let's do number 7. How many molecules are in 23.45 moles of water? What are you given? Moles of water. What are you being asked to find? Molecules of water. We start with what we're given. Over here, here's the units of our answer. If we can convert this to 1 ratio, you'd have a ratio, what goes on top. Use your good buddy, your good friend, unit analysis. Molecules go on top of water, moles go underneath. Where do you get this? 1 mole of a compound equals Avogadro's number of molecules of that compound. And therefore, 1 mole of water equals Avogadro's number, 6.02 times 10 to the 23rd molecules of water. 4 significant figures, 3. My answer is 3. And if we look at number 8, that's the same one. Let's do number 9. Ooh, NaCl, sodium chloride, table salt. How many moles are in 5.87 times 10 to the 16th molecules of sodium chloride? What are you being asked to find? Whenever you look at a problem, that's the first thing you should be able to identify. And in this case, it's moles of sodium chloride. Tea break. Boy, this chemistry is thirsty work. Let's get back to work. You're trying to find how many moles of sodium chloride. You're given how many molecules of sodium chloride. This is where you start, because that's the only thing you have. This is the answer unit-wise you're trying to get to. How do you go from here to here? You have a ratio, conversion. And how do you know what goes there? Use unit analysis. Moles of sodium chloride go on top. And what you're trying to get rid of, I don't want molecules of sodium chloride, my final answer, you put underneath. Where do you get the relationship? 1 mole of sodium chloride equals Avogadro's number of molecules sodium chloride, and that's 6.02. Remember, 1 is exact, 3, my answer is 3, and that's how you do it. Now, the next thing, you should know how to calculate Did I have a mistake? All right. For problem 10, one of your colleagues, I made a mistake and it's confirmed. It should be 1.50 times 10 to the 33rd. Bad, Dr. White. Bad, Dr. White. Don't give me a thumbs up. Never mind. But anyways, like I said, I make mistakes. Right now, because my printer's dead, I've got to buy a new one. I can't correct it. If I had my printer working, I would. All right, let's move on and see how many more mistakes I make. All right. And the question is, let's look at 14. What is the molecular weight of H2SO4? H2SO4 is called, as the name, sulfuric acid. It's probably the most, the chemical that's produced the most on a yearly basis in the United States, if not the world. In other words, there's more pounds of sulfuric acid produced in the United States than any other chemical. I'll talk more about it during the semester. Now, molecular weight, what's that? Well, if we look at important information, and this you'll be given on test 2 and the final and the other test 2, the molecular weight of a compound is the sum of all atomic weights in that compound. Summer rerun, instant replay. The molecular weight of a compound is equal to the sum of all atomic weights in a compound. And if we look at sulfuric acid, H2SO4, there are 2 hydrogens, 1 sulfur, and 4 oxygens. Remember, when you look at the periodic table, that's not what I want. Use all atomic numbers rounded off to 3 significant figures. So if we look at hydrogen, just to remind you, it's on the table 1.008, but to round that off to use on my test, it should be 1.01. If we look at oxygen, it's 15.999. That rounds off to 16.0. I'll let you figure out what sulfur should be. I'll give you 4.5 seconds. Go. I'll give you 2 more seconds. Aren't I nice today? And the answer is 32.1, which I see you people already knew. Doesn't it feel good, all the stuff you're learning? Thank you, Dr. White. You're welcome. All right, which I have here. And now, if we look at it, you add them up. First of all, you multiply them. There's atomic weight, 3 significant figures. Hydrogen, sulfur, oxygen. I'm missing a bracket there. You don't have to have it there. But anyways, remember, when you're adding numbers, you have the same number of significant figures past the decimal point as the number that has the fewest significant figures past the decimal point. In this case, 211. There shouldn't be that dot there. It should be 98.12. You round it off and you get 98.1. And that's the molecular weight. Remember, molecular weight, which I use the abbreviation MW, is the sum of all atomic weights. And we've already done these, so I'm going to move on. And now let's look at number 16. How many moles, and I could have said moles of ammonia, are in 2.345 grams of ammonia? What are we trying to find? Moles of ammonia. What are we given? Grams of ammonia. How do you proceed? Well, first of all, let's go back to important information. And 1 mole of a compound equals the molecular weight of that compound. How do you get the molecular weight? Well, we just did that. The molecular weight is the sum of all atomic weights. So this will be given to you on test number 2. I used to make students memorize it. Now I'm just testing your knowledge of chemistry, not how good you can memorize things also. And I think that's a good thing. 1 mole of a compound equals its molecular weight in grams. So if we're trying to figure out how many moles of ammonia, and we're given the weight, the only place we can start with is that, because that's all we're given. What units am I trying to get my answer in? Moles of ammonia. If I could convert it in one ratio, use unit analysis. What goes on top of the ratio? Moles of ammonia. What do I want to get rid of? Grams of ammonia. Where do I get this ratio? 1 mole equals the molecular weight. Oh, shucks, Dr. White didn't give us the molecular weight of ammonia. We have to calculate it. 3 hydrogens, 1 nitrogen. Atomic weight of hydrogen to 3 significant figures, 101. Atomic weight of nitrogen to 3 significant figures, 14.0. Do the math, add it up. 2 past the decimal, 1 past the decimal. Keep the 0, use 3 to round off. It's 4 or less, I drop it. The atomic molecular weight of ammonia, NH3, is 17.0. 1 mole of a compound equals its molecular weight. 4 significant, 3 exact number, and here's the number you get. Now, if you notice I have it written 2 ways. If you want to use scientific notation, that's fine. If you don't, that's fine. I don't know if I told you this. I have a piece of paper downstairs that's signed by the Board of Regents of Michigan State University that tells everybody I know how to do scientific notation, my PhD diploma. All right, now, this was finding out how many moles are in a certain weight. Let's do number 17, which is how many grams are 5.61 times 10 to the third moles of sodium chloride. Big tea break. Let's get back to work. What are you being asked to find? How many grams sodium chloride? What are you given? How many moles of sodium chloride? This is where you start with because this is all you got. What units are you trying to get your answer in goes after the equal sign. I think you all know what equal is. I assumed that I shouldn't. That's in math what we're trying to get to. And that's grams of sodium chloride. Use your good buddy, your good friend. Oh, yes, I will. Unit analysis. And grams of sodium chloride goes on top. Moles of sodium chloride goes underneath. Where do you get this number? One mole of a compound equals its molecular weight in grams. The molecular weight of a compound is the sum of all atomic weights. This will be given to you, but you have to know how to use it and when to use it. You do that by doing the practice problems. And now we know, where do we get the relationship of moles to grams of sodium chloride? 1 mole equals its molecular weight. You have to calculate it. 1 sodium, 1 chlorine. The atomic weight of sodium is to 3. That should be, I don't know where that 1 came out, but ignore it. Oh no, my problem set has been attacked by the dreaded 1 virus. It's enough we have to deal with COVID-19. Now we got to do the 1 virus. This should be 23.0. If you could see Dr. White, he's looking, oh, I'm so sorry. And this is 35.1 for chlorine, 35.5. Add them up, 1 pass, 58.5, 3, 3. My answer, 3 significant figures. And the last one is the same thing. And that's that. Any questions on the problem set? While you're doing that, Republica tea, wild blueberry tea. I already had my mug of vanilla almond earlier today. When did I start work this morning? It's about 5:45 I started working. Dr. White always starts early. The early bird gets the mole. Oh, is that bad? Oh, it's bad. All right. Any questions? No. All right. One of the things I raced through, and I want to go back to it, is the following. And that's limiting reactants. And that's where you run out of one chemical and that stops the reaction. So let's do one. We're just talking about sodium chloride. So let's take a look at this in case you can't read my handwriting. How many moles sodium chloride are made when you react 9.45 moles of sodium with 6.00 moles of chlorine? So what are we trying to find? Moles of sodium chloride. What are we given? 9.45 moles of sodium. That looks ugly. And right here, 6.00 moles of chlorine. Now, in order to solve this problem, what you have to do is 2 steps, and that is calculate moles water for each reactant. And I'm going to be nice and let you try the first one. Why don't you figure out how many moles of sodium, how many moles of water will you make if all 9.45 moles of sodium react? Why don't you try that out yourself? Remember, the coefficients of a balanced chemical equation give you molar quantities or ratios. And don't forget to use your good buddy, your good friend, unit analysis. I'm just asking you to do the first one, not all of them. Dr. White's being mean this morning to you, making you work hard. See everybody coming in with their answers. Usually if I were in the classroom right now, I'd be looking around and saying, remember, look up and smile if you're done. And since I can't see you, everybody is done. Give me a thumbs up. If you're done, give me a thumbs up. Thank you, people without video using. All right, I think everybody's done. Let's go ahead and do the first one. And that would be, if we come down here, we want to go for each reactant. You want to convert that to how many moles a product would make if all the reacted. And here, in this case, our product is water. We use unit analysis. Whatever we're trying to get to goes on top. Whatever we're trying to get rid of goes underneath. Where do we get this? Put the units in. Here I have moles water. Here I have moles sodium. Where do I get these numbers? I come up to the balanced chemical equation and say the coefficient tells me for every 2 moles of sodium, I make 2 moles of sodium chloride. So in here, the answer is, or the numbers are 2 and 2. Hold on while I do the math. I think I can do this. It's the same thing. Remember, these are exact numbers and don't play a role in significant figures. This was 3, this should be 3. Now, we have to do step number 2. And that would be 6.00 moles of chlorine. I see someone have a question. Hold on. Somebody's ahead of me already. At least we'll give Dr. White a chance to do it too. Times something. What do we want to get to? Moles of water Again, using your good buddy, your good friend, unit analysis, whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. Let me just check something real quick. Thumbs up, people. Can you see the screen with me working? Thank you. And now, where do we get what units? This is wrong color ink. Moles of water. What do we put down here? Moles, chlorine. Where do we get those numbers? We come up here and notice for every 1 mole of chlorine, you make 2 moles of sodium chloride. Oops, where did I get water? Somebody should have corrected me. I got water on the brain, I think. I was going to do it again. Now we're on the right track. Sorry about that. And remember, 1 mole of chlorine makes 2 moles of sodium chloride. 1 mole of chlorine makes 2 of this. I can do this one in my head. That'd be 12.0. Now, for these problems, you look at the 2. How much did you make for this with sodium? And how much would you make of the sodium chloride with the chlorine? And the lower number would be your answer. There's another way of doing this, but I found this is the easiest way for students to do it. And that's how you do it. All right, everybody unconfused now? Any questions for Dr. White? And I'd like to thank all my your colleagues who are helping out in the chat. Ooh, Dr. White was just gonna do a generation gap. I'd like to thank everybody in the peanut gallery. And none of you know where that comes from, I'll bet. Back when I was a kid, like about 5 or 6, one of the most popular shows for kids on TV was, and I didn't like it, my friends didn't, but it was very popular, Howdy Doody. Look on Google, the Howdy Doody show. And Howdy Doody, funny last name, Doody, never mind. But anyways, Howdy Doody was this little puppet, and it was live, and they had an audience of kids, and they were called the Peanut Gallery. And he'd come in, Howdy Doody. And how's my peanut gallery doing? Don't ask me. But I can say back when I was a kid, even through high school and early college, what was on TV then is much better than the garbage that's on there now. Much better. All right. And that's how you do it. Any questions on stuff I've covered so far? I went through yesterday percent yield. That will not be on a test or a final ever, but I just wanted to cover it. All right, listen carefully. First of all, tomorrow I'll go through the balanced chemical equations lab. Don't forget, you should have handed it in. If you didn't, I'll give you a 1 day, 2 day reprieve. Get it in. Normally in the semester, if we were in the lab, I wouldn't be this nice, but because of all the, how should I say, fun we're having with our problems in our society with the virus, Dr. White is being mellow. I don't know if you even know what that means. Anybody ever hear the song Mellow Yellow by Donovan? Uh-oh, I just did a generation gap. Go to YouTube and listen to it. It's a good song. I'm not going to ruin your day and sing it. But anyways, I have finished everything that will be on test 2. Now, I had planned on giving it tomorrow, but it's not fair to finish up and do practice the day before a test. And Dr. White doesn't teach that way. Remember, test number 2 will be next Thursday, not tomorrow, but next Thursday. And that means I finished everything I'm going to talk about for new stuff for test number 2. So now it's time to go on. If you look at the syllabus, it's there for test stuff that will be on test 3. I will tomorrow go through balanced chemical equations, and then next Monday I'll do the mass problems from the balanced chemical equation. You have so many grams, how many grams of a reactant do you need to make so many grams of a product? I'll go through that practice problems on Monday. Next Tuesday, wow, time's flying quick. I'll do my world famous review. First of all, how many want me to do a review for the next test? Give me a thumbs up. I see a few. I see more. Guess what? I'm still going to do it. I'll do my world famous review for test number 2. Wednesday, we'll do stuff on test number 3 material, continue on. Thursday, we'll still have our Zoom meeting, but I'll give the test like I did test 1 at about 8:45. I'll send out the password for the PDF file for that test. You'll have until Friday, 9 a.m. to get it uploaded to Blackboard. That way, if you're working or other things happen in your life, it works out better for you. Let's see. Okay. Well, it's time to move on. Let's move on. All right, let's move on to chapter 11. Let me check with my thumbs up, people. See chapter 11? Thank you. All right, chapter 11. Now we get to deal with gases. And I think you know gas is one of the 3 states of matter. And we'll talk about in this chapter some important things about gases. Now, this will never be on a test, but when you think about a gas and the behavior of a gas, what is a gas? It's particles, molecules. I can't think of any in our daily life atoms of gas. I've worked with atoms of gas, but not in our daily life, your daily life. And those particles or molecules are fairly far apart. In solids to liquids, they're closer together. Now, gas molecules are moving around very rapidly, and the particles have little effect on each other. They're sort of like running around independently until they collide. And then they're sort of like billiard balls. Have all of you either played or seen someone play pool? you know, the balls on the table and they go like this, clink. And gas molecules do the same. And as you learn, gases fill their container, they have indefinite volume. And they also have indefinite shape. All right, switches off on this, but it's still good background information. There's what's called the kinetic molecular theory of gases. And it's a series of statements explaining what is a gas. And the first one is this, again, hold on. Click, the switch is off. This won't be on a test. Gas consists of small particles, atoms or molecules that are just zooming around, moving randomly with rapid velocities. That means they're moving real fast. And another way of thinking of it is they're a collection of particles in constant motion. The attractive forces between gases, the particles of gases, can be neglected. In other words, it's almost zero. The actual volume occupied by gas molecules is extremely small compared to the volume that gas occupies. That means if I have a gas particle and another particle, they're far apart. And in between is this empty space. We're in a solid, they're really close together. Liquid, they're farther apart. Solid gas, they're way apart, even off the screen. Oh, speaking about particles of gas, when's the last time you've been outside and you felt the wind on your face? Which is I like and enjoy. Guess what? That was molecules of oxygen, nitrogen hitting you. And they were moving very, very quickly. Now, the average kinetic energy, this is a sort of a thing, how much energy they have, the speed, the force of the gas moving is proportional to the Kelvin temperature. The speed of the particles increase with increasing temperature. And we'll talk more about this. And gas particles are in constant motion and they're always moving rapidly and in straight paths unless they collide into something like you. So that's the kinetic theory of gases. And it's time to take a break. So why don't you come back at 9:55? That's when the big hand is on the 11. For those of you with digital watches, 9:55. And with that, I'm going to go stretch. I'll see you in 5 minutes. Break time. All right, let's get started again. Ring, 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 ring. I just did a generation gap. If you see the old cartoons and some of the old TV shows from the early 1800s, they'd show the school marm, teacher with a bell to get the students into class. All right, we're talking about gases. And when we talk about gases, there are key properties of gases you can measure. One is the pressure, the other is volume, how much there is. You can measure the temperature, and you can measure the amount. How much does that gas weigh? And usually when you have an amount of gas, remember gas is just a molecule, and there you can go from grams to moles. And those are key properties. Now, one of the most important properties of a gas is the pressure. What's pressure? Switches off for the screen. You don't have to know this formula. And the pressure is defined as force applied per unit area. That's the total force on a surface divided by the area of a surface. Now, I'll never ask you to do any calculations like this. Guess what? I've never done it either. Now, one way to measure atmospheric pressure is a barometer. And a barometer is a way to measure atmospheric pressure. In other words, all around us right now, gas is pushing on us. Dr. White's being silly. Well, he's always being silly, but he's having a good time today. And since you were born, from the time you were born, this was always here, you don't really feel it, but it's always pushing on you. And how do we measure that? We use a barometer. Let me ask my thumbs up people. Can you see the pictures? Thank you. Now, if you look over in the right-hand corner, the original barometer was designed by an Italian, Torricelli. And Torricelli, what he did was take a dish with mercury in there. Mercury, the element, is a liquid at room temperature. And then he had a long tube that he evacuated and took, that means take out all the air in there. And while it was still evacuated, he stuck the tube underneath the surface of the liquid of mercury. And immediately afterward, when he took his finger off, I assume, or whatever, the bottom, the mercury went up the column. Why did it go up the column? Because the pressure from the gas in our atmosphere pushed down and forced it up the column. Now the distance from where the pool of mercury is in the dish to the top of the level where it climbed, you can measure. You can measure that in millimeters, which is metric. You can measure it in inches, which is the English unit. And those are all how we get barometers. Now today, we have digital barometers. I've got a couple in my house, part of these clocks and date and all that. But the old time barometers use mercury. In case you don't know, mercury is an extremely hazardous compound that will do serious damage to you, which is why we don't use it anymore. But up till about 1980, 80, even longer, up to about 10, 15 years ago, I could go into some labs and you'd see the old mercury barometers like that. And then because of safety concerns, no lab has those anymore. They have the kind with a dial and digital or anything. Now, as you saw, you can measure the length of that column, and we call that millimeters of mercury. And that's 1 unit of pressure. Now, since Torricelli did most of the work on this, the pioneering work, to honor him. We also have the unit torr, which is short for torricelli. And 1 millimeter mercury equals 1 torr. This will be given to you on test 3, important information. Now, there are other ways of measuring. Oh, first of all, another important measurement at sea level. Chicagoland is at sea level. The atmospheric pressure, assuming there's no storms going through, is 760 millimeters of mercury. Therefore, since 1 torr equals 1 millimeter mercury, 760 millimeters of mercury, which is the pressure at sea level of the atmosphere, is also 760 torr. Now, because this number is so important, chemists gave it another unit, and that is 760 millimeters of mercury equals 1 atmosphere. Now, I have here, know this. I really should put down there, know how to use this, because I'll give you that number for test number 3. Now, there are other units that I will not be using, but we use in our daily life. Inches of mercury is what, if you listen to the weather forecast, they'll usually tell you the pressure, barometric pressure or an atmospheric pressure is so many inches of mercury. 1 atmosphere is 29.9 inches of mercury. Another one, which is used a lot, and I've used it a lot, is pounds per square inch, PSI. Sometimes you'll see a PSIG in a plant, pounds per square inch gauge, but usually it's PSI. And 14.7 PSI equals 1 atmosphere. These are all definitions. They're exact numbers. Now, let's take a look at this one first of all. If you've ever been in a car, you know they have tires. And what's in the tires? Air, or in the last 10 years, maybe not even that long, car companies, entire companies that convince people, oh, you should just put nitrogen in there so we can charge you more money. I use air. I'm a chemist, so I know better. But anyways, it won't hurt, but why pay extra money? Think about your car tires. They have gas inside of it. And you can measure your tires, and you should at least once a month. Newer cars have gauge in there. You can just look on the panel by your speedometer. And normally, like for my SUV, I keep mine at about 35 PSI, which is more than twice the atmospheric pressure. And that's why they stay inflated, because the gas is trying to get out, as opposed to if it was less than the atmospheric pressure, you'd have a flat or be flat and it wouldn't work well. So the question is, why learn about gases? 1, you're breathing 1, and 2, they're in your car tires, and a lot of other things. Now, let's go back to something important. Oh, actually, I got it on the next slide. But first, let me remind you, 1 millimeter mercury equal 1 torr. 760 millimeters mercury equals 760 torr equal 1 atmosphere. These are all exact numbers. And now let's have some practice. How many torr is 452 millimeters of mercury? Okay. So what are we trying to find? Milliliters of mercury. What are we given? Actually, what? I can do that. What are we trying to find? Torr. What are we given? Therefore, I bet you thought we were done with it. No, we're not. It's time to use your good buddy, your good friend, unit analysis. You can use it in a lot of places. See, somebody already beat me to the answer, but and some important information you should know. One millimeter of mercury is equal to 1 torr, and also (760) millimeters of mercury equals 760 torr equal 1 atmosphere, ATM. So here, this is a simple one, but I'll still use unit analysis. Here's what we start with. What do we want to get to? We'll use unit analysis. Whatever we're trying to get to goes on top of the ratio. Whatever we don't want to get rid of, or we do want to get rid of, goes underneath. This is torr. This is millimeters of mercury. And this is 1, this is 1. So the answer is, in this case, 452. Don't forget, these are exact numbers, 3 significant, 3. Let's move on to the next one. This is an important skill you should know how to do. What are we being asked to find? How many atmospheres? What are we given? How do we proceed? Well, we only have one number. If we can convert it with some ratio, what do we want our answers to be? Atmospheres. What do we use? Our good buddy, our good friend, unit analysis, whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. In this case, this is atmospheres. Down here is millimeters of mercury. Where do I get these numbers? You will be given this on test number 3, and that is 760 millimeters of mercury equal 760 torr equal 1 atmosphere. Therefore, this is 1, this is 760. Both of these are exact numbers. And now, I'll go over to my calculator, which I'm going to have to make. And the number I get on my calculator is this. Remember, we started with 8, 32, 3 significant figures, 1 and 760 are exact numbers. So you round this off to 3 significant figures. And the answer is, I'll give you 3 seconds. Time's up, 1.09. Keep the 1, keep the 0, keep the 9. Use the 4 to round off. That's 4 or less. This gets knocked down. We go back to our answer where we were. And the answer is right here. Guess what time it is? It's time for Dr. White to let you have some fun. Why don't you try and set up how many atmospheres is 777 torr? Go. When you're done, give me a thumbs up. Remember, use your good buddy, your good friend, at unit analysis. When you're done, give me a thumbs up. All right, I'll give you 8.76 more seconds. I gave you a couple bonus seconds. All right, let's do this. The question is, how many atmospheres is 760 torr? So what are we trying to find? What are we given? This is the only number we have to start with. What units do we want to get to? Atmospheres. What do we use? We use our good buddy, our good friend, unit analysis. And what do? Whatever we're trying to get to goes on top. Whatever we're trying to get rid of unit-wise, we go underneath. Where do we get those numbers? 760 torr equals 760 millimeters of mercury equals 760 torr equal 1 atmosphere. I used to make students memorize this. This will be given to you on test number 3, important information. So this is atmospheres, this is torr. 1 atmosphere equals 760 torr. And time to go to my calculator. And notice it's the number. If you go back and look, and which I'll do when I get back there, we have 777, three significant figures. 1 and 760 are exact numbers and do not play a role in significant figures of the answer. Therefore, you have to round this off to three significant figures. I'll give you 3 seconds to do that. 1, 2, 3, time's up. Keep the 1, keep the 0, keep the 3. Those are 3 significant figures. The number to round off is 2. That's 4 or less. Drop that, and the answer is 1.02. And I'm going to have to have some more fun. Why don't you do the last one on the page? How many torr is 2.1 atmosphere? You can't see it, so I'll write it down here. (760 millimeters of mercury equals 760 torr equal 1 atmosphere. Go. Anybody need more time? Going once? Going twice? All right, let's do this. What are we being asked to find? Torr. What are we given? 2.1 atmospheres. This is the only number we have to start with. If there was a conversion ratio, what answer do we want to get? Torr. Time again to use your good buddy, your good friend, unit analysis. The units you're trying to get to go on top of the ratio. The units you're trying to get rid of go underneath. What are they? Torr, atmosphere. Where do we get these numbers? 1 atmosphere equals 760 torr. Let's come over here. Notice this is 2 significant figures. These are exact numbers. Therefore, my answer should be 2 significant figures. Time to go to the calculator. This is what my calculator gives me. Now, this is a challenging number to round off, but how do you round this off to 2 significant figures? I'll give you 4.5 seconds to think about it, and then I'll do it. Now, this one might have been easier if it was in scientific notation, but I'll do both ways. All right. Now, the calculator gave me, did I write it down, 1596. To round this off, keep this, use that to round off. That's 5 or higher. Now, when the number is greater than 10, like this one, what you're rounding off and anything past it, you drop and replace with zeros. The number in front is increased by 1, and the 1 here stays. So that'd be 1,600. Now, if this were scientific notation, it would be this, and to round it off, this is the number to round off. Obviously, that's 5 or higher. I'm going to drop that and that. This increases by 1. So this becomes 1.6 times 10 to the third. And if you notice, these are the same numbers. Which is the right answer? You can use scientific notation or decimal for smaller numbers like this. If you had 20 zeros after that, please don't. And that's how you do pressure conversions. It turns out that's an important skill for you to know how to do. Not at the company you saw the pictures yesterday, but another company I worked at, a lot of the chemistry involved what's called hydrogenations, reacting molecules with hydrogen gas, H2. And that's when I had some fun because we did things that was called high pressure reactions. And there I would be at normally in the plant or in the lab, 600 PSI. In America, we measure pressure in a plant with pounds per square inch as opposed to millimeters of mercury. In Europe, they use millimeters of mercury. I've worked in European plants. Companies I work for were international. I went to Europe a lot. In fact, in the 80s, 90s, up through the mid 2000-ish, I would go to Europe 2 to 4 times a year. And when I go there, I'd stay anywhere from 2 to 4 weeks because I was a senior manager. I stayed in the best places you could stay at. That's a nice thing working for European companies. They treat you nice when you're traveling. Oh, by the way, I haven't been on in a long time because I haven't been to Europe in a while. But when I used to go there, because I worked for Dutch companies mainly, I used to go to Amsterdam, then on elsewhere, like in England, Germany, etc. KLM is one of the best airlines ever, and KLM business was awesome. But back to what I was getting to is, I would work at 600 PSI, which is roughly 50 times atmospheric pressure. In the lab, I personally worked a couple of times because it was quite dangerous, up at 1400 PSI. Remember, your car tires are only at 35 PSI. That's quite high pressure, and things at that pressure can be very dangerous. I have a minute to do it. Guess what? We're good on time. Things are working well this semester, this summer. But anyways, the high pressure lab you worked in, because the working with high pressure and metal reactors was very dangerous. Each cubicle was metal this thick, steel. And if something blew up, you'd be the only one killed. And in fact, they even had on the back wall a blowout wall that if it exploded, you could fall back and it would open up and you could get out of that room. Luckily, we never had that because we took safety precautions, a lot of them, but it was always exciting to work at high pressures. All right. Time to stop sharing and talk about something. Now, gases, where do they play an important role? Well, it turned out in the history of mankind, the Industrial Revolution was able to happen partially because of gases. Gases? Think about it. The Industrial Revolution back in the 1700s, what was an important feature of that? Having power to make machinery run. And where was that most important and first done? In England. And there you could make machinery run to make yarn, to make things which the English were known for, the wool and other cloth, cotton that they made. If you know your history, the United States, and unfortunately because of slavery, exported a lot of cotton to England. And that's how the United States settlers, our colonial fathers and mothers, made money. And unfortunately, it also set up the problems we're having in our society today, which I'm not going to get into because this is chemistry. But how did you get power? Well, first, you had a wheel near a river and it would turn, and it's called a water wheel, and that would give you energy. That's not that good. Later on, they found you could have the steam engine and later on the gas engine. And the gas engine and the steam engine both have a piston that goes in and out because gases expand and contract. So whether you're talking about water vapor, which is a gas, and I'll teach you more about it this chapter, or air and gasoline and the products made from when it combusts, which we know is combustion engine, they all deal with gas in a cylinder. Well, understanding the properties of the gas in the cylinder is quite important. And turned out certain English chemists discovered mathematical relationships with some of the physical properties like pressure, volume, temperature, amount of gases. And understanding that helped design better steam engines and later on better gas engines. And the gas engines, they're running our cars to this day. And what those mathematical relationships are called the gas laws. Now, a law is something that's always true, always true. The first law I'd like to talk about is Boyle's law. Now, you don't have to memorize this, but if you're reading a book, they'll say Boyle's law, and Boyle is the chemist who found it, and chemists have a habit of people who do great discoveries. We name those great discoveries after them. And the Boyle's law is the volume of a sample of gas is inversely proportional to pressure applied to the gas if the temperature is kept constant. Remember hand pump. I'll get to this probably next week. What the heck is that? Hold on. I don't understand that. Let's get it clear. What Boyle's law is really P1 times V1 equals P2 times V2. I don't have it on here, but let me write now. P1 is the initial pressure. V1 is the initial volume. P2 equals the final pressure, getting ahead of myself, and V2 equals the final volume. And this is Boyle's law. You will be given this. In the past, I made students memorize this. You'll also be given this important information. Remember, we're now covering stuff for test 3. And if I look at the clock, guess what? I'm out of time. With that, I'm going to wish you to have a great day. Enjoy the weather. Gay and gesund. Be healthy. And with that, I don't want to let you feel left out. Bye.